Okay, well, thanks for the introduction there, Brad, and welcome to everyone to today's webinar. We're going to be discussing the Earth test today. This will be our final webinar for the year. So thanks to all of those that have come along to the previous two. We will be looking to do some more in 2019. So if you do have any topics that you'd like us to cover, please do get in touch and let us know what you're interested in, and we'll look to set up webinars accordingly. So let's move on with the Earth test, and we'll discuss what we're going to be talking about today. So just some of the topics we'll cover. We'll show some of the most common definitions that I'll be using throughout the webinar today. We'll be talking about the ground connection itself, what its purpose is, and ultimately what it's there for as a safety feature. We'll move on to the actual testing for Earth itself, why we should perform the test, what classes of equipment we would be performing the test on commonly, when the testing should be performed, what actually is tested during the test. We'll then have a look at some of the differences between bond testing and continuity testing, and we'll have a look at some of the parameters that should be tested. We'll discuss the test connections, how to make connections during the test. We'll follow that up by having a look at some examples of the tests according to the standards. So for this particular webinar, we'll be looking at the production line test requirements. We'll have a quick discussion around 2-wire and 4-wire measurements. And finally, we'll finish up with some couple of video demonstrations. So throughout the presentation, we'll be handing the floor over to yourselves, so that we do have a couple of polls that we'd like you guys to take part in where possible. But let's move on into the body of the presentation. So some of the common definitions, we talk about Earth testing. It's also commonly known as a ground test. I guess between Europe and the Americas, we typically in Europe call it an Earth test, whereas in America it's called a ground. So those two terms are generally kind of interchangeable for this sort of testing. Resistance, we'll cover resistance a lot because ultimately that's what we'll be measuring. And that's a measurement of the difficulty encountered by a power source enforcing electrical current through an electric circuit. Resistance is measured in ohms. So when we talk about ohms or even milliohms today, that's our unit of measurement, and that's what ultimately the pass or fail judgment will be made against, how many ohms we have, or milliohms. And finally, the current. An electric current is a flow of electric charge. In electric circuits, this charge is often carried by moving electrons in a wire, and the current is measured in amps. And current is one of our key parameters within this testing area. So firstly, let's look at the purpose of the ground connection. Why do we even fit a ground connection in the first place? Well, on a product, it provides a secondary level of safety for users. So the primary level of safety within any product is generally the basic insulation. So those barriers between you and I and any kind of live parts, they're always seen as the first level of safety, and then Earth is fitted as a secondary level. So the obvious aim of the Earth connection is to carry fault current away to ground. So in the event that the insulation does break down, current will flow onto the chassis of the product. And what we want to do is that chassis then is connected to ground. Current flows away down through the ground cable, back down through the building earth, and away to ground safely, keeping the operators nice and safe. So that earth cable is important, and we obviously want that to be a low impedance connection. We want current to flow easily down through that cable for reasons I'll talk about as we kind of move through the presentation today. But we want that to be a nice, good, low resistance connection. As I said, ultimately, earthing a product still relies on a good continuous connection all the way through the building and ultimately down to the system earth and ultimately away to ground. So here we have a circuit that's in good condition, if you like. There's no damage to the insulation. So as you can see, the current flows nicely up through the product via the live or line conductor, goes across the load, whatever that may be in terms of the product, and away back down through the neutral. So we have basically a balanced supply. All the current flowing in the live is basically flowing down through the neutral. There's no issues. The operator can come along and touch the product, and there's no kind of shock hazard to them. So let's have a look at what happens in the event that something does go wrong. So firstly, let's have a look at a product here. So we have a product, current is flowing around, the chassis is made of metal, and during the production phase, someone accidentally takes a screw all the way through the item chassis and eventually pinches that onto the live cable. Now what's going to happen there is we're going to allow current to flow to the chassis. So as you can see now, current is starting to flow around the chassis. If I was to come along and touch that, I'm now connected to ground. I'm now creating a path to ground. What will happen? Current will start to flow through me and away to ground. So I've now created a shock hazard. We've created a situation where if someone was to touch this product, there's a good chance they're going to get an electric shock. Our basic insulation has failed, so our first level of safety has failed in this case. So we now need to rely on something else. And in this case, we could fit a ground conductor. Now, what happens with this ground conductor? Well, as we said before, we want this to be a nice low resistance. For those of you that joined me on the previous webinar, we spoke about effects of human contact and the resistance of a human body being of approximately 2,000 ohms. Well, as we start to progress through this presentation, we'll start to talk about ground connectors in being kind of 0.1 of something of an ohms. So for those of you that know the phrase path of least resistance, current will always flow where it's easiest to flow. And we want that easiest channel to flow to be down and away through the ground. So that low resistance channel is taking the majority of the current flow. Sure, some of it may flow through me, but if the majority of it is flowing through the ground connector, then that should help to keep me safe. So as I said, ultimately we're using this ground conductor to be the path of least resistance. In the event that a fault occurs, we want the majority of current to flow nicely away to ground via this cable. But obviously we need to prove that cable is there and fitted. So that's why we perform the test. Ultimately, we want to make sure the product is safe. If something was to go wrong, that level of safety, that level of security provided by the ground connector is there and in good condition. Obviously, by performing the test, we're also demonstrating our compliance with any kind of regional or international standards for the product that we will be manufacturing. We can use it as a measure of quality control on products. We'll kind of cover this a little bit later, but it can be used as a measure to ensure what we're sending out to customers is what we say we will be sending. We can use it as a measure of degradation. So as part of our maintenance schedule, if any of you are using routine testing as part of a maintenance schedule, maybe you repair equipment and send it back out to customers, or you're hiring out equipment to end users and you're using the test to ensure ongoing safety, we can check that ongoing reading to see if there is any degradation and therefore repair it before it becomes an issue. And the final reason we perform the test is that it also can perform part of the measuring circuit for further tests. So those of you that joined us on our webinar regarding HiPot at in November will remember that we said in some circumstances, particularly on class 1 or earth products, we can use the earth cable as the return into the instrument to measure any external current flow during that test. If that cable obviously isn't there, then we wouldn't get a good reading back into the instrument, and therefore we could be getting false failures. So the earth is also used as part of a measuring circuit when we perform future tests. So when should we be performing the testing? Let's have a look at the class of equipment. The first one we're going to talk about is the class 1 product. Now, a class 1 product typically consists of 3-core cable, unless it's kind of 3-phase, but typically we have our line conductors, we have our neutral, and we have an earth cable. The earth cable is always connected to the product's casing, and that's reliant on the earth for a safety measure. So in a class 1 product, we're relying on the earth as that secondary measure of safety. So any class 1 product, we should always be performing an earth test. Class 2 products, it's a different story. There's generally only 2-core cable, line and neutral. There's generally a secondary layer of insulation, so a double insulated, as per the double box symbol you see there. So for this, we're not reliant on a ground for safety, we're actually reliant on 2 layers of insulation for safety. So for a class 2 product, it's typical we don't need to perform an earth test, generally because there just simply isn't an earth connection that needs testing. So always on a class 1 product, we should be performing earth testing. Now, if we look at the life cycle of a product, there's generally kind of 3 times that we might be performing this type of testing on a product. Similar to the HAL test that we spoke about in the last webinar, throughout the stages of a product life cycle, we will perform an earth bond test on a class 1 product at type testing. Again, much like the HAL test we discussed at the last webinar, this will be a much more strenuous test than any other test we perform on the product. So we may be performing it at a higher currents or for much longer periods, potentially into kind of minute-long scenarios. And we really want to prove that the thing is safe by design. So once we know it's safe by design, we can then start to put the product into production. So we're now building it, and we need to perform our routine or factory acceptance testing, or commonly known as the production line test. So this is proving now that although we know the product is safe by design, we need to ensure we know that it's now been built correctly. So that scenario that I spoke about earlier, where someone screwed a screw too far into the product and kind of nicked the live cable, those are the kind of faults that we're now looking for in a routine or production line test. So it's typically a much quicker test, takes typically a couple of seconds, but we're trying to just prove that build process hasn't contributed to the product becoming unsafe. And then finally, the one we've just spoken about is that kind of maintenance testing, where you are testing a product on an ongoing basis, whether that's after a higher period, or in the kind of Europe, we do portable appliance testing. So on that ongoing kind of testing, we can use it as a method of degradation measurement. So we've kind of already spoke about this, but to protect an end user from shock, a manufacturer can really incorporate 2 key safety features. The first one being grounding or earthing, fitted to ensure that path exists to carry fault currents to ground, or insulation that acts as a barrier between live parts and the user. And as you can imagine, ground testing or earth testing is all about proving that ground path. That's what we're trying to prove at this point. So let's have a look at what is tested. Well, as we've already kind of said a few times, the point of the earth test is to check the connection between any exposed metal parts of the item under test to a ground connection. So there may be multiple points within the product that we need to test. It is used to measure the resistance of the earth cable to prove that it's both continuous and ideally of sufficiently low resistance. We'll talk about the differences between a continuous and a good low resistance measurement when we talk between continuity and bond measuring. Now, if we are testing a class 1 product, we are performing the earth bond test. It is absolutely good practice to always make sure the ground bond test or the earth bond test or continuity test is always the first test that's performed in any sequence. We need to know that ground's there, particularly if we're going to be using the ground as a return for further tests, such as the HAL. So as we've already said, failures could be indicative of problems with either the design, any of the manufacturing production processes. It could be due to incorrectly fitted or faulty components, or, as we've said, wear and tear when routine testing is performed. As a product's being used, the cable's being pulled and pinched, etc. So, over time, that could potentially make the product weak. So the earth bond test is flexible. It does have multiple kind of uses and can prove a number of things. So let's talk about continuity versus bond. Firstly, it is common that these kind of terms are interchangeable. People often talk about earth continuity and earth bond almost as being the same thing, but actually the reality is they are quite different. In general terms, a continuity test is generally there just to prove there is a presence of a connection. So there is literally a connection on the earth. However, a bond test is a bit more stringent. So the bond test can actually give us a measure of the condition and ultimately the integrity of the earth connection. So it doesn't just tell us it's there, it tells us how good the connection is, how strong that bond is, if you like. So firstly, let's have a look at earth continuity. Earth continuity is only performed as part of a routine test. So when it comes to kind of design testing or type testing, we generally will always perform a bond test because that is the one that tells us how good the connection is. So continuity testing, where it does come up, is only performed really as a routine or production test. It's sourced from a low current DC output. So we're only ever applying a low current, so we're not really stressing the product. And commonly, measured values aren't required. So a lot of the standards will simply say an indication of continuity or prove there is continuity. So something like a lamp or an audible buzzer sounding just to give continuity. If any of you've used a kind of multimeter, you know you have that continuity test where you just, as long as there's continuity, you get a buzz. That is all a continuity test generally is. For test parameters, they're often not given. So within many standards, and we'll show you some examples a little later, it's often that test parameters aren't given. The only stipulation is that continuity does exist. As we've already said, it doesn't stress the test circuit under fault conditions. We'll talk about that a little bit more when we talk about the bond test. And the other thing is, because it's a low current source, it's often less accurate and it's often prone to measurement errors. So things like contact resistance, dirt or buildup of carbon between the mating ends, so your clips or probes, if there's any kind of carbon buildup on the end of those, they can really give big kind of measurement errors when we're doing a low current continuity measurement. So on an earth bond test, that's a slightly different scenario because the high current actually kind of just blasts through the through any kind of contact resistance. So moving on to the earth bond test itself, the earth bond test now is always a part of a type test and is often used as part of the routine test. Personally, where the two options are available, if I could do one or both, I would always kind of err down the side of doing a bond test for reasons we'll cover as we move through. We're always typically using a high current to stress the connection. Most standards you'll see we're well above kind of one amp. Generally, we're above kind of 10 amps in the majority of bond times. And it will highlight faults that aren't detected by the continuity measurement. One of those being things like strands. If we had broken strands, the earth bond test will pick those faults up. We actually have a video towards the end of the presentation showing the difference when we apply a continuity current to a final strand of a piece of earth cable versus when we apply a high current bond test. So I'll show you that a little bit later as the webinar progresses. Now, the good thing for bond testing, as opposed to just a buzzer that says there is continuity, is it will display quantitative, so measured values, and also qualitative values. So you can start to really hone in on the condition of the earth connection. So imagine we're always making a product. That product is always built in the same way, and we always supply the same cable in the same length. We can start to really get a quality measure of how good that connection is once we know all those kind of values. It's also true that an earth bond measurement is generally much more accurate, and typically in most equipment that can measure bond, we can measure down into kind of milliohms. So it's much more accurate. And as I said before, it's also less prone to errors such as contact resistance, just because the high current can actually penetrate through any of that buildup of carbon and actually make a good connection. But it is worth noting that on a regular period, any kind of contact with probes or clips, you should give them a good clean with any kind of alcohol, just to make sure you are making as good a connection as you can. So let's have a quick chat about the kind of test parameters for earth bond testing. As I've said, typically continuity, there aren't many parameters that we really need to worry about. So we'll focus more on the earth bond for this. So the test voltage and the test current, it's usually defined by the manufacturing standard, and it's typical that the bond current can either be AC or DC. The seaward range of production testers do an AC earth bond measurement. So the magnitude of both, so the load voltages, typically the standard will recommend no load voltages, and they are typically less than either 6 volts or 12 volts, or typically between 6 or 12 volts, depending on the standard. Typical test currents for a bond test are generally in excess of 10 amps. Commonly, it's also mentioned as twice the rated protective current device, so i.e. your fuse. So for example, if we had a 5 amp fuse, we'd be looking at a 10 amp test, etc., etc. So that typically goes up dependent on the standard, dependent on the safety body, i.e. UL, etc., that we're trying to cover. That can be anywhere from 10 to 40 amps, typically. Test times, again, the standard typically will determine what test time you should be performing. But as a general guide, if we're performing type tests, i.e. design tests, the earth bond test is typically performed between 60 and 120 seconds. So, a minute to 2 minutes long. Production or maintenance testing is much, much quicker because we know the product should be safe by design. We're just trying to root out any kind of failures that have come into play via the production process itself or wear and tear. So it's typical that a production earth bond or ground bond test is performed somewhere in the region of 1 to 5 seconds. Now let's have a chat about pass limits. So a good test is proven by the fact that the measured resistance doesn't exceed your set test limit. So again, we'd refer to the standard. They would give us a guidance on the limit. We perform the test, and providing the reading is less than that reading, then everything's good. The test equipment itself uses Ohm's law to calculate this resistance. And we use that using our known output current, our known voltage output. And what we do is we measure the voltage drop across the 2 points that we're measuring. So the point at which the tester makes contact with the incoming earth terminal and the point at which we place the probe. So as a good example, we've taken a test, we've used a 25 amp test current, and across the 2 points, we've measured a 1.6 volt drop. So quite simply, what the test equipment does is it uses Ohm's law, so V over I, to give us a resistance value. So it takes our 1.6 voltage drop, divides it by our 25 amp test current, which gives us a 0.064 ohms or 64 milliohms. So it's important to note that our limit is a max limit. We always want to be beneath whatever value we've set for the test limit. So as I said, certain standards will suggest this limit for the resistance, and it's typical in most standards that remit is kind of 0.1 ohms. Now, again, we have to factor in the fact that certainly most products will be fitted with a supplied power cord. So again, most standards will make limit for that or make kind of reference to that. And that's either by adding a set factor, so something like 0.2 ohms, or they may say it will be 0.1 plus the resistance of the supply cord, or typically 0.1 minus any resistance of the supply cord. So in order to do that, we could do it one of two ways. We could set a limit that includes 0.1 plus our calculated resistance of the supply cord, and we can do that via tables. So there are typically tables that give us a resistance per meter for any kind of thickness or cross-sectional area of supply cable. Or we could measure our resistance of the cable first, connect it to the product, and then minus that off of the total reading and hope that that's less than 0.1. We often get asked, because most new kind of modern equipment will have a capability to add a lower limit when we're doing any kind of testing. And the question often is, well, why would I want to use a lower limit? And actually, there's two reasons you may want to do that. Firstly, it can be used as a check of the instrument output. So if we imagine we've got a piece of test equipment, now let's imagine for whatever reason that test equipment develops a fault. And that fault is that it always reads 0 resistance. Well, we live in a real world, and 0 resistance is very, very difficult to achieve, particularly when we're measuring down in kind of milliohms. So it could be seen that if we had a product, we had some supply cable, we know there's going to be resistance between the 2 points that we measure. So if for any reason our tester started to display 0 milliohms, and let's say our test equipment didn't have the capability to put a minimum limit in there, well, effectively what would happen is that's going to pass everything. It's reading 0 all the time. If the operators weren't picking up on that, then they wouldn't know there was an issue. So we would always see a good condition. But we know we shouldn't be getting 0 resistance. We know we're going to get some resistance due to the cabling. So we could set a lower limit just kind of slightly above 0 that would pick up this kind of failure condition. And therefore, if the machine did start to read 0, it would at least start to fail the test, and the operators could kind of make warning and get someone involved. Secondly, we can use it as part of quality control. So again, take for example, we have a toaster. That toaster is always supplied with 2 meters of cable. It's always built in the same way. We're always using exactly the same amount of cable. Therefore, from toaster to toaster, we should expect very little fluctuation between the resistance readings. Okay, there may be some slight, but they should be there or thereabouts. Well, in this case, we could start to set a tolerance band. So we could start to bring the lower limit closer to our upper limit, that whatever we've decided to set. And therefore, we would know if potentially the cable supply was too long, too small. So we can really use it as part of a quality control as well. So as I said, for example, let's assume the cable is cut in half. So someone's decided we're only going to supply 1 meters of cable. Effectively, our resistance reading could be as much as 50% lower than we would expect. And therefore, our lower limit would pick that up and it wouldn't go out the door because of a quality issue. Okay, so at this stage, we're just going to pause the presentation. And I just want to ask you as our attendees, does your company perform continuity measurements or bond measurements as part of your production line test regime? We'll just give you a minute or so to respond, and then we'll pick up and continue with the presentation. Okay, well, thank you for your participation in the poll. We'll have a further one a little bit later on in the presentation. At this point, I think it's prudent to kind of have a look at maybe the test standards, so we can show exactly kind of the differences between the requirements depending on the type of product that you're manufacturing. Now, what we're going to show you here is purely the routine or production line standards. So for the ones we spoke earlier about type tests, this wouldn't necessarily comply, and certainly some of the values will be different, and certainly periods, test times, etc. will be longer. So firstly, you can see for lighting applications, we've got 2 standards up there. We've got the British European or international standard, and the UL standard for lighting. So you can see in the European variant, for a production line environment, we'd be performing the test at 10 amps with a no load voltage somewhere between 6 to 12 volts. We have a limit of 0.5 ohms or 500 milliohms, and we'd only be performing the test for a second. Now, if you contrast that to the UL requirement, you can see actually there's no test current specified. We purely need to prove continuity. Now, they do give us a limit for that continuity, and they do give us a time, but in terms of test current, etc., there's no real kind of requirement for that. So we could do that at a low current DC continuity measurement. For household or similar equipment, you can see actually the story is identical. Both UL and the British European standards require that we do the test at 10 amps from a supply no greater than 12 volts. Our limit can be 0.1 to 0.2 plus the any resistance in the supply cord. Now, interestingly, for this particular standard, there's not a specified time level. The standard actually states that it should be performed for long enough for the measurement to be performed. So again, we typically say 1 to 2 seconds would be kind of all you'd need to perform that. If we look at a couple of other standards, the BSEN or UL 61010 for measurement laboratory or control equipment, you can see there for a production test, we purely need to prove that the continuity exists. Interestingly, this is the standard that C would comply to for our test equipment that we supply. However, we do like to perform a bond test because we feel it's a more strenuous and more kind of accurate reading for proving the condition of the connection rather than just the presence of continuity. And an audio visual standard here, British European standard 62911. This is a standard purely for the routine testing of audio visual or information technology equipment. You can see that their recommendation for the test current is 150% of the rating of the overcurrent device, i.e. the fuse, but no less than 10 amps and no more than 25 amps. From a 12 volt or less no load voltage. And again, 0.1 or 0.1 plus the supply cord resistance, and that should be performed for a period of time of 1 to 4 seconds. Okay, so that's what we can see the standards are calling for. Let's have a quick chat about how we actually make the test connections. So typically an earth bond test will perform or will consist of 2 connections to the equipment under test. The first connection we make is at the earth terminal, or if our product is supplied with a plug, that would be the earth pin. So that's our first measuring point. The second point then is somewhere on the chassis, some exposed or accessible metal parts of the equipment under test. So effectively, as I said earlier, we're making a connection between, let's use a plugged product as an example, the earth pin of the supply plug, all the way to the chassis of the equipment, which is then connected into the tester at those 2 points, and we measure the resistance from wherever we make the test connection. Now, it is important to note that there may be more than one earth bond test needing to be performed on a product, particularly if you have either metal joints where you may have some separation between the two, i.e. a good connection ensures that you have earth continuity, or particularly if you use earth straps. So you have your main earth terminal, and then you have earth cables branching off to different points on the product. We need to make sure that all of those points, the earth connection is sound, so we may be required to do multiple earth tests. It's also worth noting that the line conductors, live and neutral, do not form part of the test circuit. We often get asked, because the current is 150 times, say, that of the overcurrent device, then will that not blow the fuse? Well, 150% of the current potentially could blow a fuse, but because that path doesn't take it across the fuse, then there's no danger of doing that. Okay, let's have a look then in practical terms at the test connection itself. So here we have a typical product. We have a meter of some description. You can see we have our live, neutral, and ground connections. So we would take our first probe and make connection onto the ground conductor. Again, that could be the earth pin of the product under test. We would then take our secondary connector, and that would go onto the item chassis. Now, this could be a probe, it could be a clip, as you see in the diagram here. So we're just making 2 connections. Again, for those of you with the Seaward HAL equipment, you'll know that we have an output socket where we can actually physically plug a plug into the device. That effectively acts as this connection here. It acts as the ground connector connection. Okay, now let's have a quick chat about repeat testing. Like I said, let's assume our chassis is now separated into parts, and that may be plastic separations. So we need to be sure that should this live conductor or any break within the live conductors become in contact with the chassis at any point, we need to make sure that there's a ground cable there to carry that fault current away. So we may add some earth straps into the equation. So what that would ultimately mean is that we would have to perform, in this case, 3 separate bond tests to make sure that these 3 straps to earth are going to do their job and make sure that the operator or the user would be safe in the event that something was to go wrong. Okay, finally, the final kind of point that I really want to talk about is our methods of measurement. Now, there are a couple of different ways that manufacturers can measure earth continuity or earth bond or generally resistance. And that's 2 methods that typically are used. We either use what we call a 2-wire measurement or a 4-wire measurement. So a 2-wire measurement, that's a typical kind of measurement system for continuity measurements. It generally consists of 2 test terminals. You just plug 2 plugs into your tester, and that's your 2 test points. Now, what that does is it also includes the test lead resistance. We'll talk about it in a second, how the test lead resistance plays a factor in this measurement. And ultimately, a 2-wire measurement is less accurate. Now, a 4-wire measurement is more typical for kind of the bond measurement environment. Now, it typically consists of 4 test terminals. So you have 2 pairs for either side of the measurement. You have 1 pair that carries the current and 1 pair that carries the voltage drop measurement, or a sense as it's typically known. Now, in this case, test lead resistance doesn't play a factor, so there's no need to remove it or zero it out like you maybe have to do in a 2-wire measurement. And it's a much more accurate method of measurement. So where you need precise measurements, typically a 4-wire, or you may know it as a Kelvin measurement, is a much more accurate system. So let's have a quick look at how the 2 differ. Okay, so here we have a 2-wire measurement system. So those of you that have a digital multimeter with a continuity setting, for example, will know you have 2 test meter terminals. So when we take the measurement, we actually take the measurement back here at the test terminals. So the voltage drop is measured across the 2 test terminals. Now, what that ultimately means is we have to factor in the resistance of the test leads, the resistance of the product we're measuring, and any contact resistance within that circuit. So when we take that measurement, the total resistance we're going to be measuring will be the total of the resistance of the test leads, any connection resistance, and the actual measurement that we want to perform. So there is potential error within the measuring system. And if we give a good example here, good quality test leads have a resistance of about 0.02 ohms per meter. So if we have a test resistance piece of 0.1 ohms, we have 2 lots of test lead resistance at 0.02, giving us 0.04 ohms of error. If we have some connection resistance, and that connection resistance can be as high as the test leads, so let's assume it is, we've now got another 0.04 ohms of resistance, which means our measured resistance is 0.18 ohms, or effectively 80% of an error due to this test lead connections. Now, it is true that most modern 2-wire measurements do have a feature that potentially allow you to zero out the test lead resistance. So it measures the resistance as you short the test leads together and then subtracts that from the final resistance. But that does mean a kind of manual operation to do that whenever you want to take a measurement, whenever you change anything within the test leads. So there is a 2-wire measurement is more prone to errors. Now, if we look at a 4-wire measurement, it's a slightly different connection. So inaccurate ohmmeters, and again, as I said, in the Claire equipment, we use this method because it's much more accurate. Effectively, what you now have is 4 test terminals, which ultimately equates to then 4 wires of test measurement leads. The 2 current terminals carry the test current around the circuit, and then the 2 voltage drop terminals, or sense terminals as we call them, are generally placed exactly at the point where we want to take the measurement from. So typically that would be at the point of the earth pin if we're testing on a plug, and exactly at the point on the chassis that we want to take the measurement. So the voltage drop is measured directly across those 2 contact points that we make. So we don't have any kind of test lead resistance to worry about. We don't necessarily have so much contact resistance. It may be there, but the high current generally will remove that when we do a bond test. So the volt drop across the sense terminals, as you can see here where we've made the connections, is effectively the same as the volt drop across the resistance. So the test lead is not included in the measurement, which also means you can have much longer test leads without causing issues to make better connections or simpler connections to the product under test. So if you have the capability to do it, we would always recommend a 4-wire measurement. Here's a typical kind of diagram of a 4-wire measurement, particularly where probes and clips are used. Effectively, we have 4 cables and the jaws are separated electrically from one another. So the contact point is only made at the point at which the jaws come into contact with the item under test. Similar vein, if you do use something like an earth probe, contact is made at the point of the probe making contact with the item under test. So again, our recommendation would be, if you do have 4-wire measurement capabilities, certainly that would give you a much more accurate reading. If you couple that with then an earth bond test, a bond test plus a 4-wire measurement will give you the ultimate in measurement accuracy and quality measurement when you're performing earth testing on any kind of production line environment. So at this stage, again, we'd like to ask you a quick poll question to see if you guys know what you're performing your earth testing at. So quite simply, are you performing earth testing using a 2 or a 4-wire measurement technique? We'll give you a minute to just answer the question, and then we'll finish up the webinar from there. So let's go ahead and quickly set up a test parameter. So for this, we have a household item. So we're going to perform the test in accordance with IEC 60335-1. So for our earth bond test, you can already see we have a 50 Hertz test set up. We need to output a test current. Now, according to that standard, that should be a minimum of 10 amps. So let's set that to 10 amps. Now, test time is configured as long as it's needed to take that measurement. So something like a second or two would be more than adequate for this particular test. This is for the production standard, so routine testing. So let's set that to 2 seconds. Okay, and finally, the last thing we need to do is set our test limit. Now, the product itself has a supply cable, so according to the standard, we would be allowed up to 200 milliohms of resistance, or 0.2 ohms. So let's set ours to the 200 limit. Okay, so we now have 200 milliohms, and that's all we need according to the standard. So we're now ready to perform the test. So we've made our connections. The last thing to do is use our probe. So our test probe, when performing earth bond test, gives the operator some information. You can see currently the probe is flashing rapidly. That's a sign to the operator that the probe is ready to be used, and the operator can then pick this up and go ahead and use the test. It also tells the operator further information during the test. So when I start the test away, you'll notice the flashing slows down. That tells the operator that the test is in progress. And then at the end of the test, providing the test is good, the green light should illuminate solid, so we know that it's passed. If it was a failure, the light would go out. We would also have an audible kind of warning from the tester in the case that the product failed. So integrated into the test probe is also a start condition. We call it our no burn system. So it allows the operator to press the probe down, press the probe to start via a micro switch, and then maintain pressure so that no sparking will occur between the two mating points. Now that sparking could create some kind of burn marks on the product, and we obviously don't want that for cosmetic reasons. So let's put it on, and we're ready to test. So as soon as I depress the probe, the test will start. Providing the resistance reading is less than 200 milliohms, we should see a pass. And there we go. So you can see the resistance reading was 103 milliohms. Our indicator came solid to tell us that the test was passed. So everything is good with this toaster. So for this particular experiment, we're going to perform both a continuity test and a high current bond test on this same piece of cable. And the aim is to highlight the differences that the two tests can show. Now, what you can see we've done here is we've taken a piece of earth cable, we've stripped and cut away all of the strands, leaving one final strand of copper between the two mating points. Now, the aim of this is to show that whilst the continuity test will prove continuity and current will flow from one end to the other through the measuring circuit, and ultimately highlight that we do have continuity, that it won't highlight conditions where a potential failure or a potential issue can arise. Now, albeit this being kind of the extreme of the kind of conditions that you could see, what we'll hope to see here is that whilst performing the test at 200 milliamps, current will flow freely across that last strand, won't have any effect, and effectively could carry that current all day long. What we'll then do is we'll up the current to 20 amps, so we'll effectively multiply the current by 100 times for a typical kind of bond current, if you like, and we'll see what the effect of that has on the cable. So let's go ahead and start the test away at 200 milliamps. So the test has started. You can see there's no effect on the cable, it's carrying the current without issues. We'll run it for 10 seconds and everything's good, the test has passed. There's been no highlight of the poor conditioning of the cable. Now, although on this particular instance we're getting a reading of the resistance, if we use a more traditional kind of light indicator or even an audible indicator, all we would know is that we have current. We wouldn't know about this potential condition. Now, when we go ahead now and perform it at 20 amps, we should see the resistance will be much higher because that current can no longer flow freely through the conductors. And hopefully what we'll see is the cable heat up and hopefully fuse due to that excessive heat. So let's go ahead and start the test away. And you can see almost instantly the cable got hot, the cable fused, and our test equipment picked that up as a failure condition. So that highlights why really a bond test is a much better test on either a production or a type test environment to prove that you have a good earth connection.
Now we'd like to briefly introduce you to our range of industrial leading production line safety testers, the HAL series. Designed to increase productivity during tests, the HAL is a highly flexible tool for electrical manufacturers. Each HAL is capable of storing up to 6,000 test records, has the ability to download the results to a PC. Combined with a barcode scanner, full traceability of your production testing can be kept, giving you peace of mind. The HAL series is fully programmable. Test sequences can be created, stored, ensured that the product are tested correctly time after time. For those wanting automated systems, the HAL can be fully remote controlled and integrated into any system. All right. The HAL Earthbond tests have the following specifications. It uses Kelvin 4-wire measurement technique for accurate testing, programmable parameters with the test current up to 40 amps, integrated start condition with test probe, visual indication of past conditions on the probe, and a unique no-burn probe function, ensuring good contact is made and held throughout the duration of the test. Avoids scorch marks on the casing from poor contacts. As you can see on the table, all of our testers in the HAL series will perform AC high pot at 50 or 60 hertz, a DC high pot, and insulation resistance. For those that need testing the earth or ground bond of the equipment, the HAL 103 adds this feature. In addition to traditional safety testing, our HAL 104 and HAL LED range also adds the ability to perform load and leakage tests, ideal for those who also want to ensure the product is fully operational prior to shipping, potentially saving on expensive out-of-the-box replacement costs. The HAL LED is perfect for manufacturers of low-power products who want the flexibility of performing operation checks and is ideal for the LED lighting industry. That concludes our presentation. Thanks again for your participation. If you have any further questions, please use the questions tab in the toolbar and we will respond to them before we go. To contact us after the webinar, the regional contact details are listed here as well.
Okay, well, there doesn't seem to be any further questions, so we'd like to take this opportunity again to thank you all for coming. Hope you have a great holiday season, and we'll hope to speak to you in the new year.